Okay, we're going to finish our discussion of slope of the tangent line that we started on Monday. And remember that the reason we're talking about slope is we're going to be talking about a rate of change. And a rate of change is what a derivative is. A derivative is a rate of change. And the most common rate of change you've been working with is that linear relationship where it's a consistent rate of change throughout the function. But not all functions change at a consistent rate. For example, this one is increasing and then it decreases and then it increases again. So the slope of this line doesn't accurately describe how this function changes from one position to the next. So we've been using the average rate of change, which is just slope of the secant line. It just connects 2 points, and it's just how it averages out. It's not what actually happens at each location. So the average rate of change just describes what happens over a closed interval. But if we want to know what happens at one location, the rate of change at one spot, one place would be the tangent line. And the rate of change would be the slope of that tangent line at that location. Usually that's called C. So when we want to talk about the average rate of change, then that is the slope of the secant line. If we want to talk about instantaneous rate of change, then that is slope of the tangent line. Instead of writing all these words, we refer to that as the derivative of the function at a point. Now then, notice that if we're at this location, and if we want to get if this is a secant line, to get a tangent line, I've got to decrease this distance right here. I'm going to leave this guy right at the same place, going through C. So I want this to get smaller and smaller. So the length of this segment gets smaller and smaller. It gets smaller and smaller until it reaches that location. I can come up the curve from the left or down the curve from the right, just so on this little length gets smaller and smaller. If it gets smaller and smaller, the distance gets less and less. That means the distance goes to 0. That change in x, that means I'm going to decrease it until I'm right on top of a point. If I'm coming from the left and then from the right, I'm going to be looking what happens if I come from either direction. I'm going to be evaluating a limit. All right, so the definition of the slope of a tangent line is if that distance on a curve gets closer and closer to 0 at a specific location, C, is the limit as delta x approaches 0 of f of c plus delta x minus f of c over delta x. That is the slope, and the slope is the slope of the tangent line. All right, now notice it says the slope of the graph. It doesn't say slope of the line, so let's find the slope, the instantaneous rate of change at one location, at a point, and the point is at 2, 1. So the limit as delta x approaches 0 of f of, all right, now remember I'm going to be at one location, C, so my C location is 2 plus delta x minus f of 2 all over delta x. And let's plug in, keep your limit notation, don't drop it. So I'm going to plug 2 plus delta in for x, 2 plus delta x in for x. So that's 2 plus delta x minus 3 minus, and I'm going to go ahead and evaluate f of 2, which will be 1, all over delta x, limit as delta x goes to 0, 4 plus 2 delta x minus 3 minus 1, all over delta x. Minus 3 and minus 1 is negative 4, so the 4's cancel each other out. And you have 2 delta x over delta x. So the limit as delta x goes to 0 of 2 is equal to 2. So notice that the slope of the instantaneous rate of change at 2, 1 is going to be 2. Well, this is linear, so we kind of already knew what the slope was. But what do we have if we don't have a linear relationship? What if we have just a regular old function? All right. The limit is used to define the slope of a tangent line. It's defined to use, it's also used to help us with the process called differentiation. Differentiation is just taking the derivative, and the derivative is finding the slope of the tangent line. So instead of writing slope and saying slope of the tangent line every time, we just call it a derivative. The derivative, all right, which means the same thing as instantaneous rate of change, which is slope of tangent line of f at x, one location. So instead of writing slope every time, we introduce this new notation. This is called f prime. F prime means I'm taking the derivative of a function. I'm going to take it at one specific location. And then you evaluate the limit. So let's find the derivative. I'm just going to express the derivative for any location of a function. And I don't have to have it at a specific value. I can have the derivative expressed for any location on the function. So the limit as delta x approaches 0 of f of x plus delta x minus f of x all over delta x. I'm just going to keep the same notation. I'm going to plug x plus delta x in for x cubed. So this is x plus delta x cubed plus 2 times x plus delta x minus f of x cubed plus 2x all over delta x. All right, so now then I'm going to come down here and I'm going to expand using my algebra. Something to the third power. Well, you know, I don't want to do that FOIL 3 different times, so I'm going to go over here and I'm going to rewrite my Pascal's triangle so I can use it to help me do that expansion. Limit as delta x approaches 0. That would be x plus 3x squared delta x plus 3x delta x squared plus delta x. Ooh, I've got my 3 here. Q plus 2x plus 2 delta x minus x cubed minus 2x all over delta x. All right, I'm just checking my algebra, making sure I expanded everything correctly. So x cubed, 3, my exponents for this go down, my exponents for delta x go up, and 2x2 delta x minus x cubed minus 2. All right, everything looks good. Limit as delta x goes to 0. So notice my x cubes dropped out, my 2x's drop out, so I'm left with 3x squared delta x plus 3x delta x squared plus delta x cubed plus 2 delta x. Just making sure I got my algebra set up correctly. It is so easy to make an algebra mistake. These dropped out, right? And these dropped out. So, all right. So the limit as delta x goes to 0, I'm going to factor out a delta x. 3x squared plus 3x delta x plus delta x squared plus 2. Make sure I factored out that delta x correctly. Yep, okay. All right, delta x's drop out. Now I'm going to evaluate this limit. And I'm going to do a plug-in. I can do direct substitution, plug 0 in for delta x. So that would be 3x squared plus 3x times 0 plus 0 squared plus 2. So 3x squared plus 2 would be the derivative of that function. And notice now I've dropped my limit notation and just put derivative notation in. We're going to work this one together in class, plus a few other examples on Thursday after your test.